Hello, everybody, and happy snow day. Here is the lesson I should have been giving today, and unfortunately, I do need to have you guys watch this today so that we can move on because all of these snow days have put us a little bit behind. Okay, so this worksheet I'm going to give you guys the next time we have school, maybe it'll be tomorrow, is going to be all about friction and angled forces. So basically, what do we do with friction when we have forces pulling at an angle? So of course, we're going to start all of our problems with a free body diagram. We're going to resolve any forces into those X and Y components if needed, redraw our free body diagram with the components, and then write out net force equations for each direction. So that's kind of our general recipe for all of these problems and really all of the problems in this unit. Okay. Always start with the free body diagram, resolve any forces, redraw your free body diagram, then net force equations, and that'll help us get to anything we need. Okay. So in this first question, we have a 15 kilogram box being pulled across level ground by a 75 Newton force directed at an angle of 20 degrees above the horizontal. The coefficient of friction is 0.3. What's the acceleration? So starting off with our free body diagram, we draw a horizontal line to represent our surface. We have a 75 Newton force pulling at an angle of 20 degrees. Okay. Of course, there's gravity acting on our object like most. There is a normal force, and then mentions the coefficient of friction, so we can assume that there is a force of friction. So that's our first free body diagram. Now, unfortunately for us, this 75 Newton force is off at an angle, so we have to break it up into components. So those are those X and Y parts. So our new free body diagram with those components looks like Fx. So I'm calling this 75 Newton force F. Then we have an Fg. We have an Fn. We have an Fy. And we have an Ff. Okay. Now, because there is more, or there are more than two forces in the y direction, there's an Fg, an Fn, and an Fy. In an instance like this, the normal force is not going to equal Fg. So that's something that we really have to make sure we're paying attention to. So we redrew our free body diagram. Now we have to write out net force equations. So we have a net force in the x direction is ma. So in the x direction, we have the x component of the force minus the force of friction is ma. So the x component of the force we've talked about before is going to be cosine as long as the angle is with horizontal, which it is, so that's good, minus, we don't know the force of friction, so we're going to substitute in the coefficient of friction times the normal force, max, and this ax is what we're solving for because it's asking for the acceleration. So I know that the F is 75 newtons, cosine of 20 degrees. I know that mu is 0.33, and I don't know the normal force yet. Mass is 15 kilograms, and I'm looking for acceleration. So since I don't know the normal force, and the normal force is in the y direction, I'm going to go ahead and write out my y direction equation. As with most of our problems, the net force in the y direction is 0 because this box is not going to be jumping off the surface or crashing through it. So we have two upwards forces, the normal force and that upward y component. And then we have the force of gravity pointing down. And again, remember the whole goal of this equation is to find the normal force. I'm going to rearrange for the normal force. And I get Fg minus Fy. Fn, we can do mg, the y component would be the force times the sine of the angle. So that's 15 kilograms times 9.8. You could use 10 if you wanted as well. I'm just using 9.8 because why not? Sine 20 degrees. Okay, and the normal force ends up being, hold on, I got to calculate this. Probably should have done that beforehand. It's fine. 15 75 sine of 20, making sure my calculator is in degrees, and it is. So I have a normal force of 121.3 newtons. So now that I have that number, I can substitute it in where I left that blank spot before, and I can go ahead and do the math in the y direction to find the acceleration. And we get an acceleration in the x direction of 2.03 meters a second squared. Okay. So in this question, we had to use both directions because we were missing information about the normal force, even though what we were looking for was in the x direction. Okay. So a gardener is pushing a 15-kilogram lawnmower across the lawn at an angle of 30 degrees below the horizontal with a force of 50 newtons. The lawnmower moves at a constant velocity. Love that phrase. What is the coefficient of friction between the lawnmower and the grass? So remember that coefficient of friction is that fancy looking U or M. It's kind of like an M and a mu, Greek letter mu. So when it says that a gardener is pushing a lawnmower, if we think about how we actually push a lawnmower, right? Here's my lawnmower. We kind of push down on it like that. So kind of, if we were to think about it in a free body diagram, it would look like that, but that's a really bad free body diagram form, so we're not going to do that. Okay, what we're going to do instead is draw our arrow pointing down into the right. Okay, like that. Again, we're going to call that force F, which is a 50 Newton force. Okay, it says below the horizontal because we are technically below that horizontal line, 30 degrees. Okay, we also have a force of gravity, normal force, and a force of friction. Okay, again, we're going to redraw our free body diagram so that we have an x component of the force. Our y component in this case points downward because we're pushing down into the right. Force of gravity, normal force, and a force of friction. Okay. Again, we are going to have a normal force that's not equal to Fg. Okay. Excuse me. So now we're going to go right to our net force equations. Hooray. So sum of all the forces in the x direction is max. But remember, I underline that constant velocity. That tells us that the acceleration is 0, and therefore the net force in the x direction is 0. So this really equals 0, which makes our lives a lot easier because it ends up being that the x component of the force, which is the cosine, equals the force of friction. Our whole purpose is to find mu, so we have to substitute in the equation for the force of friction. So this becomes F cosine theta is mu times the normal force. This is 50 newtons, cosine 30. I'm looking for mu, and again, I'm missing the normal force, okay? And if you're wondering, that's going to be a mu k since we're moving. I think all of these are actually going to be mu k's because they're all moving, okay? So to find a normal force, we need the y direction. That's going to equal 0 because we're not jumping off of the lawn. That would be a really interesting lawnmower, though. The only upward force is the normal force, so we're going to subtract that y component and the force of gravity. It's going to equal 0. Again, we're solving for the normal force, so the normal force ends up equaling the force of gravity plus the y component of the force this time. So we're going to equal mg plus F sine theta. So it's 15 kilograms, 9.8 plus 50 newtons times the sine of 30. Just give me a second to do the math on that. So we have a normal force of 172 newtons. You can substitute that in for the normal force in the x direction equation. So we do 50 times the cosine of 30, which gives me 43, and then I can divide that by 172, which gives me a coefficient of friction of 0.25. And remember, that is a unitless number. Okay. For future reference, the only way to change that coefficient is if we change the surface. Okay. It doesn't matter if we change the mass of the lawnmower or how hard the person is pushing. That mu is always going to be 0.25. Okay. Now, question number 3, which actually says question number 4, because we all know I'm terrible at formatting. We have 2 students pulling a heavy crate across a rough surface. The first student pulls the crate with a force of 75 newtons at an angle of 60 degrees. The second student pulls with the same 75 Newton force, but at 30 degrees. The crate moves across the floor with a constant velocity. The coefficient of kinetic friction between the crate and the surface is 0.55. What is the mass of the crate? Now, when I was doing this in class, a couple of people drew 2 different free body diagrams, one with each of the students' forces. Because the students are pulling on the crate at the same time, both of their forces need to be included on one free body diagram. Okay, so it would look something like this. It gets messy, but it's fine. Okay, and then of course we have an FG, a FF, and a normal force. Okay. Okay, so when we redraw our free body diagram, I'm going to redraw it with some different colors. Okay, so we have an F1X. There needs to be a 1 there. And an F1Y. So that represents this person's force. And then we're also going to have an F2X and an F2Y, and that represents this person's force. Okay. And then on top of those 4 forces, and I'll make my dot a little bit bigger, we're going to have a normal force, and the force of gravity, and the force of friction. Okay. So everything needs to be on one free body diagram since all of the forces are acting at once. Okay. Again, we have our free body diagram, then we can go to our net force equations. If it helps, highlight the 2 different directions of forces because that'll help you figure out your free body diagrams pretty easily. Okay, so anything that's in that magenta highlighter is in the x direction. Okay. And again, in this problem, we're moving with a constant velocity, so this really equals 0. So I have an F1x and an F2x, both pointing to the right, so they're both positive, minus a force of friction equals 0. I don't really know how that's going to give me the mass, but it's fine. F cosine theta, F1 plus F2 cosine theta minus mu times the normal force equals 0. Okay, so I don't see mass in there at all, so I'm going to go ahead over to the y direction since I am looking for the mass. Sum of all the forces in the y direction is 0. It's not always going to be the case, but it is a lot of the times. We have 3 upward forces. We have a normal force. We have an F1y. We have an F2y. And then minus an FG, all equals 0. Since I'm looking for mass, and I know that mass is really hidden inside this FG, I can rearrange this as FG equals the normal force plus F1y plus F2y. So mg is the normal force plus F1 sine theta 1 plus F2 sine theta 2. Okay, so I have F1 sine theta 1, F2 theta 2. I don't have Fn, which means I need to use the x direction to find Fn. It's a little bit different than normal. So 75 newtons. These should have a 1 and a 2. Cosine 60 plus 75 newtons cosine 30 equals the mu value 0.55. I'm looking for Fn. So I just added the mu Fn to both sides so I can solve for the normal force a little bit easier. Okay, so we add 75 times the cosine of 60 to 75 times the cosine of 30. That gives me 102, and then I divide by the coefficient of friction, 0.55. That gives me a normal force of 186.3 newtons. Now I can use that over here. G is 9.8 meters a second squared equals the normal force is 186.3 newtons plus F1 75 newtons times the sine of 60 plus 75 newtons times the sine of 30. Okay. So 186.3 plus sine 60. So adding all of this together, I get 288.75. And then I'm going to divide that number by 9.8, and I get a mass of 29.5 kilograms. Okay. All right, so now the challenge for you guys. Okay, so I'm going to let you do 5 on your own, and I'll put up the answer to it tomorrow. Okay. Now, this is your favorite type because it's all in letters. There's no numbers. Okay. So the only number or only letters that can be in your answer are M, A, theta, mu, and of course G. Now with theta, of course, you can have like sine and cosine and stuff like that. Those aren't considered letters. Sine and cosine are function. Okay. Again, start with a free body diagram, resolve into components, do net force equations, do a whole lot of fun algebra. Okay. Enjoy the rest of your snow day. Thank you for watching.